All right, so before I do the examples that I have for today's note, which this lesson is really applying Newton's laws, so it's just more applications, examples basically of what we've already been doing and how they show up. This is one I hadn't added to my note, but it came up as a question from the Nelson textbook, page 83, number 2. And I did the solution here already, so I'll just kind of show you what it is because there's a really key concept here that if you get this, it can be really, really helpful. And so here's the system they gave you. You got a box with a mass of 45 kilograms, and you've got a system set up like this with uh, 3 different ropes and tension in each of them. Right? You want to determine FT1, T2, and T3. And the key to this is, well, first of all, the system is in equilibrium. So you could look at it and maybe it occurs to you to solve FT2 first, but the real thing about this, and this is an amazing thing, is anytime you've got a system or different components put together and they're in equilibrium, that is, the forces are balanced, there's no motion, right? Zero, then that means the sum on any part of it is zero, right? So you can always break that apart, and the sum of all the forces on the individual part is zero. So, like if you had, again, you've got 3 objects here, right? And maybe they're all kind of connected, but you could always break them apart. If they're not moving anywhere, then the total force on just this one object and has to be zero, right? It's just a kind of a strategy or a way of breaking it apart. It just seems really big. So basically, what you can do if you get something like this is what I've indicated: cut it, break it into 2 or 3 or whatever helps you. Cut this system right there, and then analyze this as like 2 separate things. So if you cut it right there, and you just look at, well, you just look at this part of the system right here, right? It's not moving, it's not going anywhere. So the sum of the forces on that part of the system must be zero. And so I brought that down here. So here's just another sketch of that. We know that because of the weight of the box, there's going to be a force of gravity that's mg down. And we know the only force up is the tension in the rope, right? So if we say the sum of the forces in the y direction is zero, then I'm defining up as positive just using standard notation. Then I can set those 2 forces equal to zero, and now I can solve for FT2, right? 441 in this case. And that's now the tension in the rope. I know that now. Now I can use that and I can look at the other part of this system. Since I cut it right there, I can look at this right here represents all of this part of the system over there, right? This part of the system is also in equilibrium. And you could look at, if you wanted to, you could look at these 2 parts of it where I cut it, and you could look at that as like Newton's third law, right? You could look at this like as if these were, actually there actually was a cut there, and these 2 things have been stuck together or whatever, right? It works either way. And so since I know FT2 already, now I can analyze this half of the system. And the one force FT3, you have to break it into components, right? Because it's at an angle, and I'm using, again, vertical and horizontal as my coordinate system. So when I analyze the forces in the y direction, and no, sometimes I feel like FT3, like I should write it, over here, because it's like that's the hypotenuse of the triangle, FT3, whatever that value is. Um, and so then I look at it and say, okay, well, the sine of 60, right, would be the opposite side over the hypotenuse, rearrange that, and I get FT3 sine 60. And then I can do the opposite for the x component here. So anyway, when I look at y, I only have this and that, right? Set those equal to 0, and I can find FT3. That's the first thing I do over here. I figure out that FT3 has to be 509.2. And then now that I know FT3, then I can use the X component of FT3 and FT1, which is entirely in the X direction, and set those equal to 0, because again, this thing isn't moving in the X direction either. And that's what I do down here at the bottom, right? So I wanted to just sort of walk through that solution and just show you, because I think that's a really powerful technique that you can always do on any system that's in equilibrium. You can cut it anywhere you want and look at just a piece of it, and that piece has to be equal to 0, right? If it helped me or I needed to, this second part here, I could cut that further, right? I could look at, cut this right there, or cut the rope that represents tension 3. I could cut that, and that would be my tension there. So the note here that I made, or where I was going to start, applying Newton's laws of motion, and it's basically looking at examples of what we were doing. So some key concepts to remember when you're doing these problems: objects in equilibrium, which we just saw. Forces are balanced. In other words, the sum of the forces is 0, and you can look at any direction you want, oriented any way you want if the thing's not moving. That's a kind of a convenient way to solve problems. If you have an object or objects that are accelerating, that means the forces are unbalanced. And the way generally I would look at that is analyze each dimension independently, and the sum of the forces equals ma in each dimension, right? So I think we already saw some examples like that. You're going to end up getting each component of the acceleration when you do it this way: the x, the y, and usually that's all we do. But if you did want to look at a third dimension, you would just add that to the pile, right? So I'll look at, I think I got two examples here. The first one, we've got Superman pushes a 10 to the 8 kilogram boulder with a force of 4 times 10 to the 10 newtons south. Captain Marvel with 7 times 10 to the 10 newtons west, 30 north. With what force does Mr. Brown push if the boulder does not move? Right, so I'm going to balance this thing out, right? They're both pushing on this thing with these forces. I'm going to push with a third force, and this thing's going to be in equilibrium. So I've decided, I've said, I'll just use north as positive, east as positive. And I've taken the information I've got and just sort of made or tried to sketch that, right? So I'd used F Superman here is 4 times 10 to the 10 newtons down, and the force of Captain Marvel here, 7 times 10 to the 10 newtons. But this one's on an angle. So it does say it is west 30 north. So that means if I sketch, that means this here is 30. And it looks something like that. Okay, so if I draw that in there at 30 degrees, now I know this thing is in equilibrium. So just looking at this thing, I can kind of figure out roughly where I need to draw the force that I have to apply to this thing. So from this, I would estimate I'm applying a force something like that. And this will be we'll call it the force MB, the force of Matt Brown on this thing, which is going to balance everything out so that the boulder does not move at all. It's probably goes with it saying, but just to note, the force in the up and down direction cancel out. Whatever was pushing down, gravity balances out. So, or whatever gravity pulls down, the normal force balances out. So we only have to consider the north, south, east, and west directions here. And we can kind of break these into, so I don't know what the angle will be here, so I'll just leave that as a theta. And I will say whatever that is, the opposite side will be FMB sine theta. Perhaps we're getting a little used to this now. And the horizontal component will be FMB cos theta. And don't be afraid to take an extra second to figure those out if you're, still working on that. For Captain Marvel, it's going to be similar. The X component here will be F of Captain Marvel cos 30 degrees, and the Y component will be F of Captain Marvel sine 30 degrees. In this case, I actually do know that number is 7 times 10 to the 10, so I probably could write those numbers in. If I do those calculations, I get 3.5 times 10 to the 10, because sine 30 is just a half. And in the x direction, I get 6.06. And that means my sketch is actually okay, because it was the vertical component I somewhat wondered about. But I see here Captain Marvel has 3.5 times 10 to the 10 up, where Superman is directly down at 4 times 10 to the 10. So there would need to be a net I would need to apply a force up to balance this out. So then I would look at, I think I might have enough space here, but let's sum the forces in the x direction, which has to equal 0. And that means negative 6.06 times by 10 to the 10 plus FMP cos theta has to equal 0. Which means FMB, I'll write it out. I'll basically add 6.06 times 10 to the 10 to both sides here. Yeah, so if I move that to the other side, I get 6.0. So here I get 6.06 times 10 to the 10. And that means there's not much I can do here. Since I don't know theta. There it goes. So what I would actually do here is I probably got a little ambitious here, which sometimes I do. Instead of leaving it as the finding the force itself, which you could do, like this would be a more of a math exercise. Let me just write this as, let me go back and delete what I have here. Now let's just say this is just the x component of the force. And that way I know the x component and I can piece the vector together. And if I do the same thing in the y direction, then what I'll do is, here I've got two forces here. I've got Superman down, so that means I've got negative 4 times 10 to the 10 plus I've got 3.5 times 10 to the 10. That's the y component of Captain Marvel's force. And then I'll just say plus FMBY equals 0. So I'll just leave that as like the y component that I want to find, and that way I can, like I said, I can piece it together at the end. Okay, so anyway, if I add these numbers together, that tells me that FMBY equals 5 times 10 to the 9. Right? So basically 0.5 times 10 to the 10, which would just be 5 times 10 to the 9. Okay. Now that I have the two individual components, I can look at what the actual vector is. I can say the magnitude is 6.06 times 10 to the 10 squared plus 5 times 10 to the 9 squared. And if I work out that number, it's 6.08 times 10 to the 10. And then the angle, right? I can just say the tangent of theta will be the x component over the y, 5 times 10 to the 9 divided by 6.06, which goes to theta equals 4.7 degrees. Therefore, we can say that the force that I'm applying in order to keep this thing in equilibrium is equal to 6.08 times 10 to the 10 newtons, and this would be east 4.7 degrees north. So probably the way I sketched it was a little bit off. If you go to this here, probably this angle here would be, or the angle you can see in the diagram up here, is I made it a little bigger than it probably actually would be, but it is important that the way I drew that vector, right, was from east headed north, and that's why when I did the tangent of that angle, I selected the y component and divided by the x component. All right, so in this example, we have a boy places his sister's 8-kilogram cat in a 2-kilogram box and places it on a 10-kilogram sled. Then the boy slides the sled down a snowy, frictionless hill, so no friction to worry about, which is at an incline of 40 degrees. Unfortunately for the cat, he ties 50 meters of rope to the sled and secures the other end to a post. How fast does the cat in the box tumble off the sled? Okay, so actually that means I put these numbers in here slightly incorrectly. We've got an 8-kilogram cat in a 2-kilogram box, so that means up here we've actually got 10 kilograms. If this is, if the top box there is the cat and the box it's in, that would be 10 kilograms, and the sled itself is 10 kilograms. Now, as this thing slides down the hill, it's going to slide as just one 20-kilogram mass. So it's not until the end of this 50 meters that it tumbles off. So I've just sort of sketched what this situation looks like already. You'll notice that I defined my x, my positive x, as going down the hill, and my positive y as perpendicular to the hill, right? Just because I figure these numbers are going to be the easiest to work with. They'll mean I have to resolve the least amount of vectors into their components, right? Gravity is the only one that's not in one of these directions, right? So drawing this, and I've sort of drawn it at the point where the rope, and this is kind of my rope over here, where above where it says the 50 meters, that's there. So if I want to start to solve this, I have to look at how fast this thing would be going at the end of where the rope is. One other thing here, though, I've drawn this, and you can see I put in 40 degrees for the angle for gravity. That's this angle right here. So there's gravity. Now I know that's 40. If you want to be somewhat technical about it, you can say, well, I know this and that, right? Where the X and Y where I've drawn my axes here, which I've just highlighted in green, those are perpendicular, right? If I go clockwise from my X, right? And let's see if that arrow shows up here, right? I go 40 degrees in the clockwise direction, gets me to exactly horizontal. That means if I go 40 degrees from the other one, from what I'm calling Y, and that gets me to vertical, right? Well, horizontal and vertical are also perpendicular, right? So that means those angles must be the same. Now that's maybe a bit of a more technical way of doing it, or proving that these two angles are the same. Not to say there aren't other ways. Honestly, the way I usually do it though is something I somewhat mentioned to you before, is try to think about extremes. So what I think about is like, well, if I have a really, really small incline and I have a box on here, let's say, not drawn very well on there, but this angle here, let's say this is really small, this is like 5 degrees, right? Then the angle here, right, if gravity was pulling it down, this angle would also be very small. That would be like 5 degrees. And so as I lift this thing up, like let's say I have a ramp and I can actually adjust the angle that the ramp is on, then I would expect both angles to get larger as the ramp lifts up. And that's kind of the way I've always remembered this, is just as one angle increases, the other increases. And also they would both be zero at the same time. If the incline was zero, the box would be flat and gravity would be directly down. So that's just kind of my memory trick for that. Let's call this bottom component of the of gravity Fg in the x direction, and that would equal mg times by the sine of 40 degrees, because it's the opposite side to the 40 degrees there. And then if I sum the forces in the x direction, that will equal ma, because this thing is not stationary, right? It's actually sliding down the hill. Oh, sorry. I probably could have actually figured this out, right? I know the total mass of this thing is 20, and times 9.8 times sine of 40 degrees, in which case that's just 126 newtons. So now, because I'm actually going to need that number when I sum the forces in the x direction, I've got the component of gravity in the x direction, and that's it, right? If you look at this diagram that I've got here, right? I mean, you've got a normal force perpendicular to the surface, and you've got gravity pulling it down. So the normal force and the y component of gravity balance each other out. It doesn't go like up into the air or down into the hill. It only goes in what I'm calling the x direction. So summing the forces in the x direction is really just this one, which gives me FGX, so 126 equals MA. And technically this is A in the X direction, but it's the only acceleration we get. And this thing has the total mass here is 20. So that means 126 equals 20 a in the x direction. Dividing that out, I get a in the x direction equals 6.3 meters per second squared. So that is how fast this whole thing with the sled and the cat in the box slides down a hill. So I need to know what is the velocity at the end of this 50 meters, right? And that takes us back to kinematics. And we need to look at what we've got. We know the acceleration, um, we know the distance, right? And what else? Well, what do we want here? We want the final velocity, right? We know the v initial is 0 as well. So if we know v1 equals 0, um, acceleration equals 6.3, d equals 50, and v final, or v2, is what we want. So if you look at that, probably the easiest equation to use here is v2 squared minus v1 squared equals 2ad, which means v2 squared equals, well, v1 squared is just 0, so that one goes away. And I'm left with equals 2 times 6.3 times by 50. All right, so punching that into a calculator, I get v2 squared equals 630. And then if I square root that, I get 25.1. So that's the velocity that the cat in the box and the sled is all going. And at the point when the rope reaches its full length, presumably it's strong enough to stop the sled right then and there. And so, right, law of inertia, if you will, the cat in the box continues moving at that speed, ignoring any friction between the box and the sled, which seems somewhat reasonable here. And so that gives us the velocity we want.